We are going to start chapter 6, lesson 2, which is going to be properties of rational exponents and radicals. Two learning targets is that you can use these different properties to simplify rational exponent expressions, but then also that you can simplify radical expressions as well. Okay, a lot of these properties are mostly review. I am going to go over each of the properties. But the biggest thing that is going to be complicated to some is that we are going to be using a lot more of like adding fractions, multiplying fractions, things of that nature, which I'm going to show you how to do all of that work in your graphing calculator. Okay, so properties of rational exponents. Okay, so there's a whole bunch of different properties here, and we just got to recall what we have. So the very first one is going to be a product of a power. So here you can see I have the same base, a, and I'm raising a to the n power, and then I'm multiplying it by that same base, a to the m power. Turns out that all you have to do is you're going to take that same base and you just add the exponents. So if I have, for example, something like x to the fourth times x to the sixth, that's going to be equal to x to the 10th. Okay, so just 4 plus 6 is 10. That's how I get that. Okay, so what about if I have a power to a power? Okay, so if I have a base raised to an exponent, and then that entire thing, you can see it in parentheses being raised to a second exponent, okay, you can just multiply those powers together, and you're going to get your result. So, for example, if I had something like x to the third, and I'm raising that to the fourth power, x to the third power, and that to the fourth power, well, that is going to be raised as x to the 12th power. Okay, so what about if I have a power of a product? So a power of a product would be, what if I have two numbers like a and b, and they're multiplied together, but then that entire quantity is being raised to some exponent? Well, each term is going to essentially get each of that same exponent. Okay, for example, what if I have something like 2 times x, and that is being raised to the, let's say, third power? Okay, what's going to happen here is your 2 is going to get raised to the third power because that's kind of like in my A slot, and my B is going to get raised to the third power because that's in like my B slot. Okay, so this would be equivalent to 2 to the third power times x to the third power. Okay, now in this particular situation, that 2 to the third power can be simplified. 2 to the third power, of course, is 8 because 2 times 2 is 4 times 2 again, which would be 8. So this would be 8x to the third power. Okay, we've dealt with negative exponents slightly in our previous section. But if I have a to the negative m power, so if I have something like x to the negative fourth power, that is going to be equivalent to 1 over x to the fourth. Okay, and kind of as a result of that, we've also talked about what if I have 1 over x to the negative third power. If it's in the denominator of a fraction, it has that reciprocal nature. We've talked about this in the first section. That's going to be equivalent just to x to the third power. Okay. Zero exponent, anything to the 0 power is 1. Okay, so doesn't really matter what it is. So if I have x to the 0 power, that's just going to be equal to 1. If I have 5 to the 0 power, that's just 1. Okay, there's a couple division properties. So quotient of powers, if I have the same base, a to the m power, and I'm dividing by a to the n power, well, I can just keep my base and subtract my exponents. Okay, so if I have x to the 7th power, and I'm dividing it by x to the 5th power, I get to keep that base because I have the same I have the same base, but my exponents I'm just going to subtract. So this would just be 2. Okay, and then lastly, power of a quotient. So power of a quotient is similar to like product of a power, where if I have some quantity with two different bases dividing by each other, each base is going to get that exponent essentially. So here, if I have, let's say 3 over x, and I'm raising that to the fourth power, that will be equivalent to 3 to the fourth power over x to the fourth power. Okay, now 3 to the fourth power can be simplified, so let's go ahead and figure out what that is. 3 to the fourth power is going to be 81. And then x to the fourth power is just simplified. So this whole thing would just be 81 over x to the fourth. Okay, now that was a very, very quick summary of all of these different properties that we're going to use. And in general, you've seen these before in the past. So I'm going to try my best to go ahead and summarize what property I'm using, but we're kind of relying on you at least recalling a few of these, specifically like when do we add them and when do we subtract them. Okay, so here I have just 5 problems that I'm going to go through here. Okay, and what we want to do is we want to simplify each expression. We're going to consider something simplified when it has as little bases as possible, the least amount of bases. So if I have common bases, I would like to combine those if possible. Okay, so let's go ahead and take a look at what that's going to look like. So here, example 1, I have 7 to the 1/4 power, and I am multiplying that by 7 to the 1/2 power. Okay, I have common bases here, and I'm multiplying. That tells me I'm going to be using a product of a power. Okay, so that is the very first property that we dealt with on the table. So this is going to be equal to 7 to the, well, I need to add my exponents. So if you're not fantastic at adding fractions, you can take 1/4 and you can add it to 1/2 to get 0.75, and I'm requiring you to have it as a fraction in fractional form, so this would be to the 3/4 power. Okay. Now, before we check to see if that's my final answer or not, I want you to see whether these answers simplify into something nice and neat. Because let's say this simplified into 5. I would want you to write 5. That's the simplest form. So we can go ahead and check this. We can take 7 and we can raise it to the 3/4 power. Okay, it looks like it's not going to simplify into anything nice. So we're going to go ahead and consider this simplified, because when you reduce it down to one number, it's an irrational number and you can't write that. So this is like the exact answer. Okay, so number 2. Number 2, I have 6 to the 1/2 power, and I'm multiplying it by 4 to the 1/3 power. Now, unlike the previous example where I could just add the exponents and combine them, I could not do that to this one because the bases are different. Okay, so what I can do is I can go ahead and, or take each of these squared. So essentially, since this would be our product of or power of a product, okay, even though there's 2 different bases, the whole thing's being squared. So that means I am going to get 6 to the 1/2 power, and I'm going to raise that to the second power. Then I'm going to multiply that by 4 to the 1/3 power, and that's going to get raised to the second power as well. Okay, so essentially each term inside the parentheses is going to get that second power. Okay, and then now I just have 2 problems that are powers to a power. Okay, so 1/2, or 6 to the 1/2 power raised to the second power. Well, what would I do? Power to a power means I would multiply. I would multiply each of these exponents. So 1/2 times 2 is just 1. So here I get 6 to the first power. Okay, and then 4 to the 1/3 power raised to the second power. Okay, 4 to the 1/3 power raised to the second power. This would be 4 to the 2/3 power. Okay, so 6 to the first power is just 6. 4 to the 2/3, we're pretty sure that may not simplify, but we should check. So 4 to the 2/3 power is again, some long irrational number. So we're just going to go ahead and consider 4 to the 2/3 power just simplified. So this expression is simplified as 6 to the first times 4 to the 2/3 power. Okay, number 3. Number 3 is actually quite similar to number 2 because they're each, we have a product to a power. Okay, so we're having a product of a power. So here we can go ahead and, just like the previous problem, we can take the second power and apply it to everything inside the parentheses. So I'm going to do the exact same thing here. I'm going to take each power to that to each term. Okay, so here I'm now going to have 4 to the 5th power, and that's going to be raised to the negative 1/5 power. Then I'm going to multiply that by 3 to the 5th, and that to the negative 1/5 power as well. Now I'm in a similar situation as I previously was in. Okay, I have power to a power and a power to a power. We just multiplied. Here we're just going to multiply also. So 5 times negative 1/5 is negative 1. So now I have 4 to the negative 1st times 3 to the negative 1st. Okay. So now I can go ahead and I'm going to actually continue my work over here so I have a little bit more space. Okay, so now we have a negative exponent. We need to know, what do we do with negative exponents? Well, essentially, if it's on the bottom of a fraction, we move it to the top of the fraction. If it's on the top of the fraction, we move it to the bottom. Well, there's no top and bottom here. That implies that it's on the top. Okay, so this is going to turn into 1 over 4 to the 1st times 3 to the 1st. Okay. Now, though I have different bases, 4 to the 1st simplifies just into 4. 3 to the 1st simplifies just into 3. So this is just the bottom of this fraction just turns into 1 times 3. Or 4 times 3, which is just 1 over 12. So this answer is just simplifies into 1/12. That's the most simplified form. And again, we reduce this down into a nice, neat number because it reduced into a nice, neat number. Okay. So what can we do with number 4? Number 4, we're looking at this and we're dividing. Okay, so we have the same base and we're dividing. That means that I can just subtract the exponents because the bases are the same. But this top one doesn't really have an exponent. It just has 5. So if it just has 5, what's the implied exponent there? It's implied to be 1. Okay, so now what we can do is we can just go ahead and subtract. Okay, we have the same base to a power and we're dividing. That means I can just subtract the exponents because the bases are the same. All right, so if you're not fantastic with adding and subtracting fractions, you can take 1 and subtract 1/3. Okay, and when you get your answer, you can go to math fraction, and it will simplify it for you. So we get 5 to the 2/3 power. Okay, so 5 to the 2/3 power. We want to make sure that that doesn't simplify into any nice, neat number like 4 did. And it does not, but we can go ahead and check. 5 to the 2/3, again, comes out to some irrational number, so we're just going to leave this as it is. Okay, 5. 5, we have different bases, okay? We have different bases, and each of them are being taken to the 1/3 power here. So, but if you look at like our previous problems, just like when I had a power of a product, when I have a power of a product, here's very similar in which I have a power of a quotient, because I'm dividing. So I have a power of a quotient. So I can take this second power and I can apply it to the top and the bottom of this fraction. So I'm going to take 42 to the 1/3 power, and I'm going to raise that to the second power. And then I'm going to take 6 to the 1/3 power, and I'm going to raise that to the second power. Okay, just like our previous problem, we have a power to a power. So we can just multiply. Okay, so we're going to get 42 to the 2/3 over 6 to the 2/3 power. Okay, now here is an interesting situation because we have different bases, but they're both being taken to the 2/3 power. So even if you have different values, or different bases like 42 and 6, and they're being raised to the same power, you can actually kind of pull that power out. It's actually the reverse of what we did here. So we can actually say, hey, this is the same as 42 over 6, and that whole thing being raised to the 2/3 power. And that's because even though the bases are different, they're being raised to the same power. Okay, so then since they're being raised to the same power, I can pull that power out. And this is convenient for me because it turns out 42 divided by 6 is just a nice, neat number. And that is just 7. So I get 7 to the 2/3 power. Okay, and then we want to check to see if 7 to the 2/3 power simplifies. It does not. Okay, and so then that means this here is just my simplified answer. Okay, all of these here are the most simplified form of their respected problems. Okay. The thing that's going to make this difficult is we're gonna have layered problems. So if you look at 5, we're using multiple properties all at once to simplify it. We're using power of a quotient, okay, and then we're using power of a quotient, and then we're using power to a power, then we're using power to a quotient again, then we're just dividing to get our answer. Okay, so you're going to need to really have a intricate knowledge of these properties that, should have been hammered. Some of the basic ones were done in like your pre-algebra class, and then, we should have worked quite hard on these properties in Algebra 1. So we're just elaborating upon them by giving you fractional numbers. Okay, what I want everybody to do is go ahead and pause the video. Okay, and when you try A through D on your own, and then when you're done, go ahead and unpause it and check with me how you did. So I am assuming that you've already done these problems and you're just trying to see how you did here. Okay, so these ones I have the same base, and I'm multiplying. So that means I could just add the exponents here. Okay, so I'm going to get 2 to the, and then 5/2 power. Or, yeah, 5/2. No, 5/4 power. Okay, so 2 to the 5/4 power. Okay, we should check to see if 2 to the 5/4 simplifies. So 2 to the 5/4 power. Okay, and it looks like it does not. Okay, so we just get to leave this as my answer. Okay, letter B, we're going 3 to the 1st over 3 to the 1/4. Okay, we have the same base, so we can simplify by just keeping our base and subtracting the exponents. So here we're going to get 3 to the 3/4, because 1 minus 1/4 is 3/4. And that is going to be our answer as well. It doesn't simplify much beyond that. Okay, C, we have a couple of different things going on. The first is that each of these are going to be having the power of a quotient. So we're going to apply the 3 to the top and the bottom part here. So this is going to be equal to 20 to the 1/2 power, and that to the 3rd power. And then we're going to have 5 to the 1/2 power, and then that to the 3rd power as well. Power to a power, meaning that we can just multiply the exponents. So we're going to get 20 to the 3/2 power over 5 to the 3/2 power. Now that we have the top and the bottom mostly simplified, they each have a 3/2 power. So we can kind of go backwards and pull out that 3/2 power. And that allows me to simplify 20 over 5, which is 4. And then 4 to the 3/2 power, we should check there because we know that the 2 on the bottom is a square root, and it's possible, since 4 is a perfect square, that we get some answers here. To just get 8. Good. Technically, it would be plus or minus 8, right? Because we're taking it to an even root, which is what we covered in 6.1. Okay, letter D. Letter D is going to have a product. We're product, power of a product here, because we have two different bases and they're each being taken to the third power. So that means I can just take each part and take it to the third power. Okay, so then now we have power of a power, so 1/3 power to the third power. We just multiply those. So we get 5 to the first power, and then here we would get 7 to the 3/4 power. They don't have the same base. They don't have the same exponent. There's really not much more we can do with that, meaning that this is mostly simplified. Okay, so that is our rational exponent and some of their properties. Okay, we have some properties that involve radical symbols. Okay, so we're going to let a and b be real numbers and n be an integer greater than 1. Okay, so it looks like we have a product property, meaning that if I have the nth root of two terms being square rooted, I can split that up. Or similarly, if they're split up, I can condense them into 1. Either way. So, for example, if I have the third root of 2x, I can split that up and say that's the third root of 2 times the third root of x. Okay, and we can do that as convenient to us. So there's two different ways to remember, like just like our power of a quotient, power of power properties, or power of product properties is I can take this and I can split it up. Or if they're split up, I can condense them back together. Like that's how these properties work. They go back and forth from each other. Okay, so similarly, if the quotient property is basically the same. So I could have, let's say, the fourth root of 7 over x. That is equivalent to the fourth root of 7 over the fourth root of x. Okay, and again, if they're together, I can split them up if that's convenient to me. Or if they're split up, I can condense them down together, again, if that's convenient to me. Okay, so we're going to go ahead and consider the following things simplified. A radical is simplified if when the following conditions are met. Okay, no radicand, or the inside here of our radical symbols, can have perfect nth powers as factors other than 1. So if we're taking the square root of some number, if a factor of 4 is in there, it's not simplified unless that factor of 4 has been taken out. Okay, no radicands contain fractions. Okay, and no radicands appear in the denominator of a fraction. Okay, so when we're looking at these properties and we're trying to simplify these, we often want, we need to know what our perfect powers are, or our perfect fourth powers, or our perfect third powers. Now, using the sheet that I gave you in the previous section, we have a list of the first several perfect squares and the first several perfect cubes. In general, though, we're going to have to probably do a little bit of writing to figure out whether it's a perfect fourth power or fifth power, because I don't have those listed out for you. Okay, so feel free to continue to use this sheet, especially if it's a perfect cube or not. Okay, so what we can do here is, again, we want the least amount of radical symbols available. We want no perfect powers in them. And we want no radicals in the bottom of a fraction. Okay, so as I'm looking at this, number 6, we have the third root of 12 times the third root of 18. Okay, so as I'm looking at my perfect cubes, I need to identify whether any of these perfect cubes divide evenly out of each of these. And it looks like no, right? Because our first one is 8 of any significance. And 8 doesn't divide into 12, and 8 doesn't divide into 18. So we can actually go ahead and condense this down into the third root of 12 times 18. Okay, so then I can actually simplify this, right? We just did the reverse of the product property. Instead of taking a thing and splitting it up, we can have it split up and reduce it down into one thing. So now we can actually just take 12 times 18. Okay, so now we have the third root of 216. Okay. Okay, so now we can take the third root of 216. Now we want to take a look at our sheet here and find out whether 216, if you look on our cube sheet, is indeed a perfect cube. Its root is 6. Okay, so we can actually just say that, hey, this is just 6. As simple as that. Okay, well, what about 7? 7, we're looking at this. We're looking at fourth rooting, the top and the bottom. So we want to take a look at our first handful of perfect fourth powers. So we're going to take a couple look at our couple first perfect fourth powers. Now, the first one is always 1, right? Because 1 to the fourth power is just 1. Okay, so then we want to look at the second one, 2 to the fourth power. Well, that is 16. Well, 16 is not going to divide into 5, and I'm pretty sure 16 doesn't divide into 80. Well, it does. Okay, it does. So what we can do is we can take the fourth root of 80, and we can split it up. Now, we can say that this is the same as the fourth root of 16 times 5. Okay, how did I get 16 and 5? Because I identified the fourth root, my perfect fourth root, as 16. And when I divided 80 by 16, I got 5. Okay, well, we can split this up. We know that our radical property says that we can go ahead and split this up. And we can say, hey, it's the fourth root of 16 times the fourth root of 5 divided by the fourth root of 5. Okay, so now I have a common factor, right? I have the fourth root of 5 divided by the fourth root of 5. Those are simply going to cancel each other out. And so now I'm left with this just being the fourth root of 16. The fourth root of 16, well, what's its root? Now, you can type that in your calculator. You can go 16 to the 1/4 power, as we learned in the previous section. Or you can think about, well, when we started listing our perfect fourth powers, we did 1 to the 4th power to get this. We did 2 to the 4th power to get to 16. So this is just going to be equal to plus or minus 2. All right, because it's evenly rooted, so it's going to get a positive and a negative result. Okay. So 6 and 7 were kind of nice because they simplified into nice, neat numbers. 8 and 9 are not going to work out so nicely for us. Okay, so what we want to do is we want to take a look at the cube root of 135. Okay, cube root of 135. The first thing we should do is check whether that's a perfect cube or not. Okay, and 135, it doesn't look like it is. So what we want to start doing is start checking some of our perfect third roots. Okay, or our perfect cubes. Okay, we know 1 to the third power is going to be 1. Let's go ahead and check 2 to the third power. Okay, that's 8. Okay, and we want to check, does 135 divide by 8 evenly? No. So then we want to check our next number. So that'd be 3 to the third power, which is 27. Then I want to check, does 135 divide by 27? It does. Okay. So this is going to break up into the cube root of 27 times 5. This is the exact same way that we simplified square roots in chapter 4. And I think we simplified some cube roots. We basically split it up into perfect powers times non-perfect powers, if you recall. Okay, because then now this radical can be split up. Even I took 135 and I split it up into 27 times 5. And then that will allow me to go cube root of 27 times the cube root of 5. We know what the cube root of 27 is because we got 27 by going, well, this one was 1 to the third, this was 2 to the third, this is 3 to the third. So its root is just simply the number 3. Okay, and then the cube root of 5 can't be simplified, meaning we can just write it as the cube root of 5. Okay, so our answer for this one is simplified when I go 3 times the cube root of 5. And that's considered simplified. Okay, because we have no perfect cubes in the root symbol. Okay, we have no symbol occurring in the bottom of a fraction. So we are set. Okay, let's do number 9. Number 9, I have a perfect or fifth power. So we're looking at perfect fifth powers here. Okay, and so as I'm looking at this, we have a fraction, and really I just cannot have a perfect perfect fifth power. I can't have a radical symbol on the bottom. So we need to think about how we're going to deal with this. Okay, the first thing that's probably going to be helpful for us is try to find perfect fifth powers. So we know 1 to the fifth is going to be 1. Let's go ahead and try 2 to the fifth. That's 32. Okay, and I think that this is going to be convenient because the only thing I have to worry about is getting rid of that radical symbol in the denominator. If I can get rid of that, then it's essentially simplified for us as it is. So I need to think about what can I multiply 8 up by to get 32. So let me rephrase that. What do I have to multiply 8 by so that the result is 32? So hopefully you're thinking about that to yourself and you're saying 4. So what I can do is I can take this expression and I can multiply it by the fifth root of 4 over the fifth root of 4. Okay, and I have to do this to the top and the bottom because this here is just the number 1, right? Fifth root of 4 divided by the fifth root of 4, that's simply just the number 1. Okay, for the same reason I can cancel out the fourth root of 5 divided by the fourth root of 5 because that's just 1. Here I'm multiplying by that. Okay, so let's see what happens when we do that. Well, we get the fifth root of 7 times the fifth root of 4 over the fifth root of 8 times the fifth root of 4. Okay, our product property tells me that even though these are split up, I can condense them together. So I can get 7 times 4. So this top part is going to be equivalent to the fifth root of 28 over the fifth root of 32. Now, how did this help me? Well, this actually did end up helping me quite a bit because now look at the bottom of our fraction or the bottom of our denominator. It says the fifth root of 32. Well, we've already determined that 32 is a perfect fifth power, and we know its root. What is its root? It's 2. So this is going to simplify into the fifth root of 28 divided by 2. Okay, and this is considered simplified because no radicand has perfect nth power, so 28 doesn't have any perfect fifth powers that are divisible into it. Okay, it contains no fraction, so there's no fraction on the inside of my radical symbol, and no radical symbol appears in the denominator. And we have simplified it in a way that there's just a whole number in the denominator. Okay, so when we have these problems that you're dividing, you are going to be looking to scale this up so there is a perfect nth power. Here, we're trying to split it up so you can find what the perfect nth power is that will allow you to split it up. Okay. Why don't each of you pause the video and go ahead and try F through I. f through I and see how you can do. Okay, so I'm assuming that you've already paused the video and have tried f through I, and you are just interested to see how you did. Okay, so we're taking the fourth root of 27 times the fourth root of 3. So I need to identify the first couple fourth powers that might help me out here. 1 to the fourth power is 1, and then what is 2 to the fourth power? It's 16. Okay, let's do 3 to the fourth power. Okay, we're already at 81. Okay, and so this go ahead and is giving me a good place to stop because I'm larger than, 81 is larger than both of these numbers, so obviously none of those are going to divide into those. So let's just go ahead and condense these together. I can say that this can be the fourth root of 27 times 3. And the fourth root of 27 times 3, well, that simplifies just into the fourth root of 81. Okay, and we know what the fourth root of 81 is because I found that 81 is a perfect fourth power, and its root was 3. So this is going to simplify into plus or minus 3. Okay, so here I'm looking at perfect third powers. Okay, so let's identify our first few perfect third powers. 1 to the third power is 1. 2 to the third power is 8. Okay, so I want to check whether 8 is going to divide out of 250 or not. Oops. Okay, and it does not, as you can see. So then let's go ahead and go 3 to the third power. So 3 to the third power is 27. So I want to check if 250 divides by 27. It does not, so we're going to go 4 to the fourth power to get 256. Or no, 4 to the third power, my bad, to get 64. That doesn't divide into 250, but I'll check for everybody at home. Okay, that doesn't work. So then we're going to go 5 to the third power to get 125. Now 5 to the third power does divide into 125. So what does that mean? I can split up 250 into the cube root of 125 times 2 over the cube root of 2. I can split up that top cube root of 125 times 2 into the cube root of 125 times the cube root of 2. Okay? And then we find out that that cube root of 2 is going to cancel each other out, to find out that this is just equal to the cube root of 125. And we know that its root is 5 because that's what I had to take to the third power to get 125. Okay, let's go ahead and do H and I. H and I says that H and I, we have to do a little bit of work. And these ones aren't split up for me, so, and 104 is not a perfect cube. So let's go ahead. We actually have our perfect cubes listed out over here, so there's no need to go ahead and do that again. I'm just going to go ahead and list them. 1, 8, 27, 64, and then I'm not even going to write 125 because I already know 125 is more than 104, so we would have gone too far at that point. Okay, so I just want to see which one of these numbers divides into 104. So I'm going to take 104 and I'm going to divide it by 64. That doesn't work, so I'm going to take 104 and I'm going to divide it by 27. Okay, and then I'm going to take 104 and divide it by 8, and I get 13. So again, I can split this up into perfect cubes and non-perfect cubes. So we're going to go 8 times 13. 8 times 13 is 104. And then I can split this up into the cube root of 8 times the cube root of 13. The cube root of 8 is 2 times the cube root of 13. And then this is just considered simplified because there's no perfect cubes that divide into 13 evenly. So it's just done. Okay, so you're always looking for perfect cubes or perfect whatever power that divides evenly into it. Okay, so I can't have a fraction in my radical symbol, so I'm going to need to split that up. So this is going to be the cube root of 3 over the cube root, or the fifth root of 4. Okay, so this one here, I'm dealing with fifth roots, and I do not have access to like a table of perfect fifth powers, so I'm going to go ahead and start listing my perfect fifth powers off. Okay, so 1 to the fifth power is 1. Let's go ahead and do 2. So 2 to the fifth power is 32. All right, I really don't have to go any further because I know I can multiply 4 by a number to get to 32. What number do I have to multiply 4 by to get to 32? It's 8. So that means I need to multiply the top and the bottom by the fifth root of 8. Okay, when I multiply the top and the bottom by the fifth root of 8, I can combine them together. 3 times 8 over the fifth root of 4 times 8. I'm going to continue my work up here. 3 times 8 is 24, so I got the fifth root of 24 over the fifth root of 32. And this is perfect because that fifth root of 32, okay, we know what the root of it is. It's 2 because I took 2 to the fifth power to get this. So this simplifies it into the fifth root of 24 over 2. And then that is just my answer. All right. We still have quite a ways to go here. So let's go ahead and move to the next little section here. Okay, we're going to use conjugates to simplify expressions involving sums or differences of square roots. So this kind of goes back to like our difference of squares and difference of cubes. Essentially, what we just need to know is that these are what we consider conjugates of each other. So if I have any term plus another term and it's involving square roots, the conjugate of that is like the two same terms are the same, but then we subtract instead of add. Or if I have subtraction, I do addition. Okay, and this is going to help me use conjugates to simplify. Okay, because I can't have a square root symbol in the bottom of my fraction. We've just talked about that, how we can't have that. So what we can do is we need to identify what is the conjugate of 5 plus the square root of 3. It's 5 minus the square root of 3. Just like here, 6 minus the square root of 2, the conjugate of that would be 6 plus the square root of 2. Okay, and how is this going to help me? Well, this is going to help me by, I can again multiply by 1 in a weird looking way. That is just the conjugate. Okay, again, this is just the number 1 because 5 minus the square root of 3 divided by 5 minus the square root of 3. This is just the number 1. So I haven't changed the value of the expression in any means at all. Okay, the top one here, we would just have to distribute. So this would just end up being 1 times 5 minus the square root of 3. But the bottom is going to be a little more complicated. So we have two terms. Let's go ahead and just use our box method of multiplication that we've used all year and all last semester as well. 5 plus the square root of 3. 5 minus the square root of 3. So we can go 5 times 5 here is 25. Then here, 5 times the positive square root of 3 is just 5, positive 5 times the square root of 3. 5 times the negative square root of 3 is a negative 5 times the square root of 3. Negative square root of 3 times a positive square root of 3. Well, square root of 3, square root of 3, square root of 9. Square root of 9 is 3. So, but 1 positive, 1 negative, this is just going to be minus 3. Okay. So, here, if you look, these are opposites, so these just cancel. So what's left over? Just 25 minus 3. Okay, so then we can distribute here this 1. Well, distributing by 1 just results me in 5 minus the square root of 3. And then 25 minus 3 is 22. And that's our answer. As you can see, these are equivalent to each other. The original equation and our expression and this are equivalent to each other. This is just considered simplified because there's no square root symbol in the denominator, that we've done some work to get rid of it. Okay, so what I need to see from you is like this step here of you understanding what the conjugate is and multiplying by 1 in a form that utilizes that conjugate. So we'll be grading on being able to see exactly that. So why don't you all take a moment and try letter J on your own and check it with me when you are done. Okay, so like the critical part of this is understanding what the conjugate of 6 minus the square root of 2 is, and that's 6 plus the square root of 2. So I can multiply the top and the bottom by 6 plus the square root of 2. Okay, and it has to be 6 plus the square root of 2 because that is the conjugate of 6 minus the square root of 2. Okay, so what do we get here? Well, we're going to have to multiply 3 times. Multiplying fractions are just straight across, so 3 times 6 plus the square root of 2. So we're going to have 3 times 6 plus the square root of 2. And the bottom we're going to have to do a little bit of work for, so we're going to use the box method of multiplication. Six plus the square root of 2. 6 minus the square root of 2. So 6 plus the square root of 2. 6 minus the square root of 2. 6 times 6 here is 36. 6 times the positive square root of 2 is positive 6 square roots of 2. 6 times negative square root of 2 is negative 6 square roots of 2. Negative square root of 2, positive square root of 2 is just negative 2. Okay, and then again, we're lucky. We're actually not lucky. This is done entirely intentional, that these are opposites of each other. That's exactly why you multiply by the conjugate, is because these values cancel each other out. And so you're just left with 36 minus 2. Okay, so we have 36 minus 2. Okay, and so then we can distribute here. 3 times 6 is 18. 3 times the positive square root of 2 is positive 3 square roots of 2. This whole thing is going to be divided by 34. And even though these are divisible by 2, 34 isn't divisible by 3. So that just means that this is our simplified answer. And I understand that it looks just as complicated as the original one, but again, it's not considered simplified unless that radical symbol is removed from the denominator completely. Okay. So let's go ahead and do some more simplifying. Okay, so these ones are going to be hopefully a little bit easier. That it's kind of like combining like terms essentially. So if I look at 11, 12, and 13, I just want to condense these down to the least amount of terms as possible. So when I look at 11 here, I have a sneaky 1 hidden out here, right? It's like a hidden 1. So I have 1 times the 4th root of 10 plus 7 times the 4th root of 10. Well, if I have 1 4th root of 10 here and I have 7 4th roots of 10 here, how many 4th roots of 10 do I have completely? I have 8 of them, right? I have 1 here and 7 here. So altogether, this is just going to simplify. You're just going to combine your like terms into 8 4th root of 10. Okay? And that's just our answer, because this 4th root of 10 can't be simplified. Similarly, it works with rational expressions or rational exponents also. So if I have 2 times the 8 to the 1/5 power, and I'm adding to it 10 times 8 to the 1/5 power, well, I'm adding those together, and I have the same base and the same exponent. That means they're like terms. I can just combine these together. So I have 2 times 8 to the 1/5 power and 10 more of those exact 8 to the 1/5 power. I just have 12 of them all together. So again, we can just kind of combine these like terms together to get 12, 8 to the 1/5 power. 13 is a little more complicated though, because I'm taking the cube root of 54 and I'm subtracting the cube root of 2. This is not, I need to be very clear, this is not the cube root of 52. Because that's just not how our radical symbols work. I need to get them to be like terms. So let's take a look at the cube root of 54. Let's see if we can simplify this just like we did on the previous page. The cube root of 54, well, let's see. let's try to find some perfect cubes, right? Let's try to find some perfect third powers. 1's the first one. 2 to the third power is 8. Let's go ahead and see, does 54 divide by 8? It does not. So what about the next one? 3 to the third power. 3 to the third power is 27. So does 54 divide by 7? Or 27? It does. So we can go ahead and split 54 up into the cube root of 27 times 2. We're subtracting that by the cube root of 2. Well, the cube root of 27 times 2 is the same as the cube root of 27 times the cube root of 2. We're subtracting that by the cube root of 2. Well, the cube root of 27, well, we know what that is. Its root is 3. That's exactly how we found it. So now we have 3 cube roots of 2 minus, there's like a sneaky 1 here, right? There's a sneaky 1 cube root of 2. So I have 3 cube roots of 2, and I'm taking away 1 cube root of 2. This just means altogether there are 2 cube roots of 2. So even if the radicands are not alike, you might be able to simplify it and then find out that once you simplify it, they have alike radicands. Okay? So you can only combine these together when your radical symbols are the exact same with the exact same number, or your rational exponents are the exact same base with the exact same exponent. Exact same base with the exact same exponent, you can just combine them together. Radical symbols are the exact same root with the exact same base. You can combine them, and that's the only time you can. Okay, why don't you all pause the video, try K, L, and M all on your own, and see how you did with me. Okay, so I'm looking at 7, or K, and I have 7 fifth roots of 12, and I'm taking away 1 fifth root of 12. Altogether, that means that I have just 6 fifth roots of 12. Okay, L, I have 4 9 to the 2/3 power, and I'm adding to it 8 9 to the 2/3 power. My base is the same with the exact same exponent in each, so I can just add them together. I have 4 of them here, and I have 8 of them here. Altogether, that means I have 12 9 to the 2/3 power. Okay, so I'm looking at M, and I have the third root of 5 plus the third root of 40. And these ones do not have I have the same root, but I don't have the same radical or radicand. So I need to do some work to see maybe can I simplify it down to get the same radicand. So here I have the third root of 5. Well, I need to split 40 up, but it would be helpful if I knew my perfect cubes. We did some perfect cubes before to find 1, 8, and 27. But 8 does divide into 40. It divides into 40 quite nicely into 8 and 5. Okay, so that means I now have the cube root of 5 plus the cube root of 8 times the cube root of 5. Okay, so this means I have 1 cube root of 5 plus 2 cube roots of 5. Because cube root of 8 is 2. So I have 1 cube root of 5 plus 2 more cube roots of 5. Altogether, I have 3 cube roots of 5 altogether. Okay. So the thing that's nice is once you get used to simplifying these radical symbols as we did here, it ends up paying quite a few dividends here. So in a problem like this, we have a variable. That's really the only extra thing that we've added is that I need to split up the number into perfect cubes and non-perfect cubes and the variable into perfect cubes and non-perfect cubes. Okay, so let's take a look. So here, again, we want to split it into perfects and non-perfects. So let's start listing perfect cubes. Perfect third powers. So we get 1, and then we know 8. 27, and then 64. I'm just listing this off my, I'm assuming at this point you know how to get these perfect cube powers. Well, it turns out that 64 is a perfect cube, so we're going to get the cube root of 64 times the cube root of, turns out y to the 6 is a perfect power, third power, right? So it's a perfect third power only if if the exponent is a multiple of that number. Okay, 6 is a multiple of 3, so that means y to the 6 is a perfect third power. Okay, what's the root, cube root of 64? The cube root of 64 is 4. The cube root of y to the 6 is y squared. So that's just my answer. Okay, what about this one here? Here, it's not split up, and we want to. So let's go ahead and take the 4th root of x to the 4th over the 4th root of y to the 8th. Okay, I've identified x to the 4th is a perfect power because 4 is a multiple of 4. Y to the 8th is a perfect power, so because 8 is a multiple of 4. So what does that mean? That means the 4th root of x to the 4th is just x. And the 4th root of y to the 8th is just y to the 2nd power. Okay, so this one and the previous one, there was no simplifying into perfect squares and non-perfect squares at all because all of these ones ended up being perfect squares or perfect 4th powers, perfect 3rd powers. Okay, now we're going to get into some ones that don't have perfect third or powers in them. So I'm taking the 5th root of 4 times a to the 8th times b to the 14th times c to the 5th. So I need to start identifying what are perfect 5th powers and non-perfect 5th powers. This is the one where we have to split it up. Okay, so we want to split this up into perfect 5th powers and non-perfect 5th powers. So let's look at 4. Okay, so if I look at my numbers that are perfect fifths, I would get to 1. And then the next number I would get to is 32. So that means I cannot break up 4 into a perfect power times a non-perfect power. Meaning that 4 is just going to be categorized into the non-perfect 5th power parts. What about a to the 8th? A to the 8th, well, it's not divisible by 5, but I could split it up so part of it is. For example, I can split up a to the 8th into a to the 5th, which is a perfect 5th power, and a to the 3rd, which is a non-perfect 5th power. So how am I going to split up b to the 14th? I want to split it up into a b power that has a multiple of 5 and then another b that isn't. So how would I do this? I would split this up into b to the 10th, because 10 is divisible by 5, meaning that there is b to the 4th left over. Then c to the 5th is just a perfect 5th power, because 5 is divided by 5. Okay, and then all we have to do is take the roots. A to the 5th, the 5th root of a to the 5th is just a. The 5th root of b to the 10th is just b to the 2nd. And the 5th root of c to the 5th is just c. And then this whole part is designed that it can't be simplified. So then that's just going to be multiplied by the 5th root of 4, a to the 3rd, b to the 4th. And this is what's considered simplified. Okay, let's look at 17. Well, 17 has a problem because the denominator is in has a cube root in it, and it can't be there. So I need to think about, just like I did in the previous problems, I did it with whole numbers. What would y have to be taken to as a power? What power would y have to be taken to so that it's a perfect cube? Well, as long as that number is a multiple of 3, it's considered a perfect cube. So that means the next largest perfect power of y would be y to the 9th, because 9 is divisible by 3. So I can multiply this by a sneaky looking 1, and I can multiply it by the cube root of y. Let's see what happens there. So on the top, I would just get x times the cube root of y. And then here, I would get the cube root of y to the 8th times y. Okay, x times y. And then here, since they're both cubes in the same base, I can put them together. Okay, well, the top is not going to be able to be simplified, so I'm going to leave it like this. But then this simplifies into the cube root of y to the 9th. All right. The cube root of y to the 9th is a perfect cube because y is a multiple, or 9 is a multiple of 3. Okay, so its root would just be y to the 3rd. So we would get this as x times the cube root of y divided by y to the 3rd. Okay, so 18, we have a quotient problem here, meaning that if I have like terms, I can divide the bases. Okay, so when I have a quotient problem like this with multiple things, I'd like to just go ahead and split it up into the parts that can be simplified. So for example, I'm going to go 14 over 2. I'm going to go x and x to the 3/4. I'm going to go y to the 1/3. And there's nothing that pairs with y, so I'm just going to put a 1, because you can multiply by 1 at any time you want. And then here, I don't have anything that multiplies with z, so I'm just going to go ahead and put it with 1 also. And now this just turns into a problem that can be solved in parts that's very consistent with the very first thing that we did on this problem. So 14 over 2, simplify into 7 over 1. Okay, x divided by x to the 3/4. Well, that's a quotient, so we would subtract the exponents. 1 minus 3/4 is 1/4, so this would be 1/4. 1. Y to the 1/3, there's nothing that needs to be simplified to that, so we just get to leave that alone. And z, 1 over z to the negative 6, it's below and it's negative. We need to bring it above to make that exponent positive. It's got that reciprocal nature. Okay, and then we just multiply straight across. If we multiply straight across on the bottom, it's all 1s, so we just have to do the top. 7, x to the 1/4. Y to the 1/3. Z to the 6th. Okay, 19. 19, we have common square roots. 5 plus the square root of y plus 6 plus the square root of y. We just get to combine them. The radicands are the exact same with the same root. So this is just going to be 11 square roots of y. Okay, so we're looking at 20. 20 is going to be the last one. And I have 12 times the cube root of 2 times z to the 5th. Okay, and so I'm identifying z to the 5th as being able to broken up into two parts that are going to be a perfect cube and a non-perfect cube. Okay, so z to the 3rd times z to the 2nd is going to be z to the 5th, but z to the 3rd is a perfect cube, so that's why I'm separating it out. Okay, the same thing is going to go for this one here. 54 can be broken up into a perfect cube and a non-perfect cube, and our perfect cubes, and our perfect cubes are going to go ahead and be 1, 8, and 27. 27 is a perfect cube, so I'm going to break the 54 into 27 and 2. And z to the 2nd is not a perfect cube, so I'm going to leave that alone. Okay, so now I can take out those perfect cubes. Well, what is the cube root of z to the 3rd? Well, it's just z. Okay, and then 2 and the z squared are not perfect cubes, and they can't be simplified, so I'm just going to go ahead and leave it alone. Okay, then here, the cube root of 27 is 3, and 2 and z squared are not perfect cubes, so I cannot simplify those. All right, as we look at this, now I have like radical, or same roots and like radicands. I can subtract those. So I have 12z times the cube root of 2z squared, and I'm taking away 3 of those exact same things. That means I'm left with 9z times the cube root of 2z squared. Okay, so that is the last page of instruction. What I want you all to do is do N through Q on the next page, and then you can go ahead and check it with me when you are done. All right, so I'm assuming you paused the video and you're just here to see how you did. Okay, so I'm looking at N, and N is the cube root of 27 times q to the 9th. Those are both perfect cubes. Since they're both perfect cubes, I just got to take the cube root. So the cube root of 27 is 3. The cube root of q to the 9th is q to the 3rd. And I knew q to the 9th was a perfect cube because its exponent is divisible by 3. Okay, so then I'm looking at this one here. It's not split up, and this is one I like to personally split up. So I would take the 5th root of x to the 10th over the 5th root of y to the 5th. Both exponents are divisible by 5, so that means they're perfect fifth powers. So the 5th root of x to the 10th is x squared, and the 5th root of y to the 5th is y to the 1st. Okay, P. P is a problem where we're doing a quotient problem and there's lots of parts, so I'm going to split that up. Okay, so let's go ahead and split this up with 6 and 3, x and x to the 1/2, and y to the 3/4, and y to the 1/2. So 6 over 3 is going to simplify into 2 over 1. X to the 1st divided by x to the 1/2, I would subtract those exponents. So then I would get x to the 1/2. Y to the 3/4 divided by y to the 1/2. Okay, again, same base, and I'm dividing, so I would subtract these exponents. Use your calculator if necessary to get y to the 1/4 on top. Okay, all of the bottom is just going to simplify into 1, so I just get 2x to the 1/2 times y to the 1/4. Okay, last one. I'm taking the square root of 9w to the 5th, and I'm subtracting w times the square root of y to the, or w to the 3rd. I'm talking about square roots here. Whenever there's no number here, it's implied square roots. So I need to go ahead and split this up. Okay, so it looks like I'm going to say perfect square, 9 is a perfect square. And how can I break w up so that it's a perfect square and a not, or w to the 5th, so that it's a perfect square and a non-perfect square? Well, I can go ahead and say w to the 4th times w. W to the 4th is a perfect square, and w is not. But when I multiply them together, I get w to the 5th. And I'm going to take away w times the square root of w to the 3rd. I need, again, split that up so that I have w, a perfect square and a non-perfect square. So I can split that up by saying w squared times w. Okay, square root of 9 is 3. The square root of w to the 4th is w to the 2nd. Then times the square root of w. And I'm subtracting, well, w times, well, this is the square root of w squared. Well, that's just w. So I'm going to get w times the square root of w. Lots of w's. Well, w times w is going to be w squared. So here I have 3w squared times the square root of w. Take away w squared times the square root of w. So here I have like terms, 3 times w squared times the square root of w, and I'm taking away 1 square root, or 1 w squared times the square root of w. So I have 3 of those here and 1 of them here, and I'm taking away that 1. That means I'm left with 2w squareds times the square root of w. Okay, long lesson, lots of properties. This is going to take some time for you to master all of this different kind of stuff and identifying the different properties that we are going to be doing. Okay, but that's more than likely why we split it up among multiple days. So what I would do is go ahead and move on to the homework, and I'll see you next time for 6.3.